Section 3.4, Motion in Space. In this section, we're going to talk about describing motion in space, and specifically we're going to look at the tangential and normal components of acceleration as well as projectile motion. We are going to skip the Kepler's laws of planetary motion, but I suggest you read through the book and see if you can understand the notation for that application. It's cool, but we're short on time. In Calc 1, we learned that if we have a function that represents an object's position, taking the first derivative of that function would represent that object's velocity, and then taking the derivative again would represent the acceleration of the object. The same thing is true when we represent position of an object using a vector function. So say we have some vector function r of t. The first derivative of that would be velocity. We could call that v of t, or we could just call it r prime. And then the second derivative of that would be acceleration. We can call this a of t, or r double prime. And then lastly, if we wanted to talk about speed of that object, we would use a scalar function. This is not the same thing as the vector function v of t. This speed, v of t, is a scalar function, and it's representing the magnitude of the velocity vector. Now, just to show you how this would work on vector functions, we're going to do an example here. We have a vector function r of t. This represents an object that's moving in space over time t. If we wanted to find the velocity, we would just take the first derivative. I'm going to use the component notation here. So we would have 2t for the first component. Then we'd have 1/2 5 minus t squared to the negative 1/2 times negative 2t for the second component. And then the second derivative would give us our acceleration. So we're going to take the derivative again of the function r. So that would be 2 in the first component. Now, before we take the derivative of the second component, I want to point out that the 1/2 and the negative 2, they're going to divide off. So that would look like just this. So we could use a product rule here if we'd like, which is what I'm going to do. And then I need to multiply that by negative t. Now we can probably clean up a little bit in this y component of our acceleration vector. So let's go through and see what we can clean up. I've got a double negative here, so those would become positive. My 2 here divides off with my 2 here. I can rewrite this as t squared. That's a little better. And then over here, I can just make this minus that. All right. Not too bad. So we found the velocity as a function of time, and we also found acceleration as a function of time. Now we need to find speed. Speed, remember, is the magnitude of that first derivative of r. So to find speed, we'll find the magnitude of r prime. And this cleans up. I won't go through the messy algebra of it, but this will clean up. And let's just leave it written like this. It doesn't get much nicer than that, so we'll just leave it that way. So we did part A. We found velocity, acceleration, and speed, each as a function of time. Now let's move on to part B, which basically says sketch the curve along with the velocity vector. All right, if we wanted to sketch the curve, maybe first we would draw some axes here. Remember that t is measuring time, so we're going to let the horizontal axis be time, and then we're going to let the path be defined by the vector function. So we need to pick a few values of t that we can plug into our function here to generate the vectors that will give us the path for r of t. So maybe we'll start at something like t equals 0, 1, 2, 3, 4, 5. If we plug 0 into our function, then we get the vector 0, comma, root 5. And root 5 is just a little bit larger than 2, so let's say that this is 1, this is 2. So when t equals 0, the horizontal, t should not be our horizontal axis. Sorry, t is a parameter, and it is helping us generate points for the coordinate plane x, y. So when t equals 0, we get the vector 0 in the x direction, root 5 in the y direction. So this would be like the vector straight up the y-axis like this and generating that point. And then if we were to use the next t value, maybe t equals 1, that would give us the vector 1, comma, root 5 minus 1, which would be 1, 2. So this vector would look like 1 in the x direction and then 2 in the y direction. So this vector is going to point to this point. And then if we did another point, maybe we do 2, that would give us the vector 4, comma, 1. So we go 4 in the x direction, up 1 in the y direction. The vector function would be pointing to this point. And if we did 3 for t, we would get the vector 9. Oh, that's not going to work. You see what happens here? If I plug in 3, I do get 9 for the x component, but in the y component, I would have an undefined component function. So we actually can't go further than that. We can, however, see that our path is connecting kind of like this, and so that's a pretty good description of our path, and it's definitely traveling in this direction as t is increasing. So we've sketched our path by generating just a few vectors and connecting our points here. It doesn't need to be perfectly precise, but we do want to sketch the velocity vector at time t equals 1. So that's going to be the velocity vector that happens at this point. If we come back to our velocity vector, r prime, we can plug t equals 1 into r prime. We'll get the vector 2, comma, let's see, we have negative 1 over the square root of 5 minus 1 squared. It would give us negative 1/2. This velocity vector will travel 2 in the x direction, negative 1/2 in the y direction. So that vector looks like this guy.